Hi, my name is Alex Yu. I am a professor of data science and artificial intelligence. Today I will discuss the quantum dawn, when encryption meets its greatest challenge. As you can see, I am ready for the quantum leap. Are you ready? For decades, digital security has rested on the shoulders of mathematics. Every password, financial transaction, and confidential cloud file is protected by encryption schemes so complex that even the fastest classical supercomputers would need millions of years to crack them. But quantum computing, once a thought experiment of physics, has now moved from theory to laboratory demonstration. The geopolitical race for quantum advantage. Quantum computing is no longer an isolated experiment. It's a geopolitical race with profound technological and security implications. In the United States, companies like Google and IBM are setting benchmarks. Google, for instance, first made headlines in 2019 when its Sycamore quantum processor achieved quantum supremacy by completing a specific random circuit sampling task in 200 seconds, a calculation it claimed would take a classical supercomputer 10,000 years. A claim that was later debated but solidified the field. More recently, Google's quantum computing team introduced the Willow chip, achieving a verifiable quantum advantage using a new algorithm called quantum echoes. This algorithm, which implements an out-of-order time correlator, OTOC, demonstrated a performance roughly 13,000 times faster than the best classical algorithm running on a top supercomputer for this specific verifiable task. IBM has outlined an ambitious roadmap toward quantum-centric supercomputers. IBM is shifting from simply increasing qubit counts toward building modular quantum classical systems capable of tackling real-world problems. Starting around 2023, it introduced its quantum utility milestone and the IBM Quantum System 2 architecture, which combines multiple quantum processors with classical control and middleware to optimize hybrid workloads. Across the Pacific, China is advancing rapidly through state-backed institutions such as the University of Science and Technology of China, USTC, which unveiled the Zhejiang photonic and Zhuangzi superconducting processors, each claiming quantum supremacy in specific tasks. Startups like Origin Quantum are commercializing hardware with its 72-qubit Wukong processor and even offering quantum cloud access. The result is a tense but fascinating dual-front race, one driven by Silicon Valley innovation, the other by China's coordinated national strategy, each pushing closer to an era that could upend all digital security as we know it. The quantum leap. From bits to qubits. In classical computing, a bit must be either 0 or 1, an unambiguous state much like a light switch that's either on or off. Quantum computers, however, work with qubits, which can exist in a superposition of states. Schrödinger's cat, the famous thought experiment of a cat that is both alive and dead until observed, is often used to illustrate quantum superposition. The story of Schrödinger's cat comes from a thought experiment proposed in 1935 by the Austrian physicist Erwin Schrödinger, one of the founders of quantum mechanics. He invented it not to explain quantum theory, but to criticize how strange and counterintuitive it sounded when applied to everyday objects. Here's how the story goes. Imagine a cat sealed inside a metal box. Inside the box, there's also a tiny amount of radioactive material, a Geiger counter, which detects radiation, a vial of poison, and a hammer mechanism. If even a single atom of the radioactive material decays during the next hour, the Geiger counter will trigger the hammer to break the vial, releasing poison and killing the cat. If no atom decays, the cat remains alive. According to quantum theory, until someone opens the box and observes what happened, the radioactive atom is in a superposition. It has both decayed and not decayed at the same time. Because the atom's fate determines the cat's, this means the cat, too, would be simultaneously alive and dead, a bizarre and unsettling situation that seems impossible in our everyday world. While the Schrödinger's cat captures the mystery of quantum uncertainty, it's more of a philosophical illustration than a physical one. A more helpful way to conceptualize superposition is a spinning coin. While it spins, it's not strictly heads or tails but a blend of both possibilities. Only when it lands, when a measurement is made, does it settle into a definite outcome. This ability to occupy multiple states at once allows quantum computers to explore many possible solutions simultaneously, giving them a vast computational edge for certain tasks. Entanglement adds another layer of strangeness and power. When two qubits become entangled, their states become deeply linked, such that changing or measuring one instantly affects the other, no matter how far apart they are. A rough analogy is a pair of perfectly synchronized dice. If you roll one and see a 3, you immediately know the other must show a 4, regardless of distance. Einstein famously called this spooky action at a distance. In quantum computing, entanglement enables qubits to work together in coordinated ways, creating correlations that classical systems can't replicate. Together, superposition and entanglement form the foundation of quantum advantage, the ability to process information in profoundly parallel and interconnected ways. This enables parallel computation on an astronomical scale. A modest increase in qubit count translates into an exponential leap in processing potential, so much that a few hundred qubits could simulate complexities beyond the reach of all classical computers combined. Crucially, physical qubits are extremely fragile and subject to decoherence, loss of quantum state, from environmental noise. Achieving the stability required for cryptographic attacks means physicists must build logical qubits from thousands of these error-prone physical qubits to create fault-tolerant systems. This complex engineering challenge of error correction is the biggest scientific and engineering bottleneck today, which is why the cryptographically relevant quantum computer remains years away. Breaking the unbreakable. Quantum versus classical encryption. Our current encryption schemes, RSA, ECC, and AES, are designed around problems classical computers can't feasibly solve. RSA, for instance, depends on the difficulty of factoring huge prime numbers. But Shor's algorithm, designed for quantum processors, can factor large numbers exponentially faster, dismantling the very foundation of RSA and ECC. Likewise, Grover's algorithm can accelerate brute force attacks, having the effective key strength of symmetric encryption. Once a fully error-corrected, large-scale quantum computer is built, even unbreakable codes could fall in minutes. Implications for cloud security. Cloud computing's entire trust framework relies on cryptography, from securing connections via TLS, SSL, to authenticating users, and encrypting stored data. Once quantum computing matures, this framework could collapse. The notion that data in the cloud is safe would become obsolete. Moreover, harvest now, decrypt later strategies are already being used. Adversaries can collect encrypted traffic today, store it, and decrypt it in the future when quantum tools become available. Imagine the exposure. Classified archives, financial ledgers, medical histories, all suddenly laid bare. The race toward quantum-resistant security. As quantum computers grow more powerful, they threaten to break many of today's encryption systems, the same ones that protect our online banking, emails, and government data. To prepare for this, scientists are developing a new generation of safeguards known as post-quantum cryptography, PQC. These are encryption methods designed to stay secure even when quantum computers arrive. The U.S. National Institute of Standards and Technology, NIST, has been leading this global effort, and by 2024 it finalized the first official standards. Among the chosen algorithms are Crystal's Kyber, which helps two parties safely exchange secret keys, and Crystal's dilithium, which verifies digital identities. Unlike current encryption, which relies on math problems that quantum computers could easily solve, these new methods use lattice-based puzzles developed by Ukraine-born IBM researcher Vadim Lyubashevsky. These complex geometric structures are believed to be resistant to quantum attacks. Alongside PQC, another defense takes a completely different path: quantum key distribution, QKD. Instead of relying on math, QKD uses the laws of physics to protect communication. Because observing a quantum particle inevitably changes it, any attempt to eavesdrop on a quantum encrypted message immediately reveals itself, like a burglar triggering the lights just by stepping into the room. Google has begun testing PQC in Chrome, and major cloud platforms like AWS and Microsoft Azure are rolling out hybrid encryption systems that combine classical and quantum-safe techniques. Yet, global migration to PQC is an enormous task. Every device, certificate, and system in the digital ecosystem must be upgraded or replaced. A quantum reckoning, or a quantum opportunity. While quantum computing could shatter digital security, it also opens doors to breakthroughs in chemistry, materials science, logistics, and medicine. The same power that threatens encryption could revolutionize problem-solving across industries. The challenge isn't the technology itself, it's whether humanity can adapt fast enough to secure the digital world before quantum systems reach full maturity. The quantum age forces us to confront a new reality. The very algorithms that secured the internet for decades may soon become relics. Quantum computing doesn't just demand better encryption, it demands a rethinking of digital trust. We must build systems that can evolve as fast as the threats themselves. The following are some thought-provoking questions for your reflection. If quantum computing can unlock every encrypted secret, will privacy become an outdated concept, or evolve into something entirely new? Who will ultimately lead this quantum revolution? The US with its innovation-driven ecosystem or China with its unified national strategy? Will collaboration or competition define the next phase of technological progress? And most crucially, can humanity balance scientific advancement with ethical responsibility before the code is cracked? What's your take? Are we heading toward a quantum apocalypse or a quantum renaissance? Share your thoughts below. If you found the video informative, please like, share, and subscribe. Thank you for watching. Mahalo.